So after having learned about balancing equations, classifying equations, predicting and balancing products, writing ionic equations, now it's time to practice. And that's what this lesson is about. Let's see if we can finish this equation, and if there are such, write the complete and net ionic equation. Let me remind you of just a couple of things here as you solve this problem. Elements that are by themselves are only bonded to themselves. Elements that are by themselves or only bonded to themselves have a zero oxidation number. Okay, there's no charge. All right? If you have an ionic compound that's aqueous, it does split up. If you have an acid that's aqueous, it does split up. No other compounds are going to split up in an ionic compound or an ionic equation. Everybody got that? Whenever you do split them up, the resulting ions stay aqueous. They split up because they're aqueous and ionic, or aqueous and acidic, and the ions that you get out of it are also aqueous. All right? So we're going to have a little guest teacher here. Not a little guest teacher, but a guest teacher, okay, who's going to solve this problem for you. All right, so what he's doing is showing where the iron is going to go during this displacement process. If you look at your list of, let me find it here on the reference. I don't have one. Here we go. If you're in an honors class, you're going to be using the standard reduction potentials chart. Okay, and if you look at the standard reduction potentials, you can see that iron, down here somewhere, there's iron, Fe, is more active than the hydrogen in an acid. There's the H plus going to H2 over here. Okay? Now, it's only the iron 2 that will displace the acidic hydrogen. Iron 3, which is up here someplace, there it is less active than the acid hydrogen. So it can't, iron 3 cannot displace the hydrogen in acid, but iron 2 down here can. Okay? So whenever you displace the hydrogen, the product is going to be a version of iron 2, because only iron 2 can displace the hydrogen. Go ahead. So he has balanced the iron compound. He has one iron and two chlorates, because the chlorates have a 1 negative charge. And chlorates are always soluble. So because your acid on the left is aqueous, that means there's water around. And so the chlorate compound on the right, the iron 2 chlorate, will also be aqueous because there's water around and it does dissolve. Anytime you displace a hydrogen ion in a single replacement reaction, you get hydrogen gas. And that's why he's listed the hydrogen on the right-hand side as H2 with the physical state symbol of G. And he's doing the atom inventory now. He's counted up all the atoms on both sides, and he found out that there was not an even number or the same number on both sides. So he's using coefficients to balance equations. All right, so now this equation is balanced, and he's ready to write the complete and net ionic equations. Don't forget to show your physical state for the hydrogen ion.
You're right.
Okay. So the iron solid is still an iron solid, and it has no charge, so we don't put any charge numbers on that. But the acid, the chloric acid, splits up into its separate ions. Acids, if they're aqueous, are going to be listed as separate ions in the complete equation, the complete ionic equation. All right, so that's your complete ionic equation. Slide over a little bit so they can see the whole thing. He didn't break them up. The chlorate ion here doesn't break up. Okay, it stays together on both sides. It's the same thing on both sides. Right? Alright, same instructions here. Finish the equation. If a net and complete ionic equation are possible, you need to write those as well. Aluminum, if there's going to be a reaction, aluminum is going to go with sulfate, right? I'm not going to try to balance anything until I figure out if I have a driving force. Okay? Hydrogen is going to go with bromine. I'm not going to try to balance anything unless I have a driving force. Okay? Driving force for double replacement reactions is the formation of a solid, the formation of water, or the formation of a gas. Okay? If you don't have one of those three, you don't have a driving force. Okay? So if I look on the solubility rules, I see that sulfates are almost always soluble, while there are some exceptions. Aluminum is not one of the exceptions, so this is aqueous. Bromides are almost always soluble, while there are some exceptions. Hydrogen is not one of them. So, because there's no solid being formed, there's no water molecules over here, and there's no gas, this is no reaction. For single replacement reactions, the driving force is the fact that you have a more active element by itself that can replace a less active element in a compound. We just did that up here. More active element is iron. The less active element in the compound is the hydrogen. So in a single replacement reaction like this, iron in the form of iron 2 can displace the hydrogen in an acid. Let's try this one, folks. I have an ionic compound here and an ionic compound here. Subscripts like this do not automatically travel because they're not part of a polyatomic ion. Subscripts like this one on the sulfate do automatically travel because it is part of a polyatomic ion. It is also the case with this 3. It's part of the polyatomic ion. It automatically travels. So the silver is going to go with the sulfate. We're just going to put them together over here and see if we have a driving force before we try to balance the formulas. And we're going to put the hydrogen with the chlorate, and we're going to wait to balance the formula until we see if we have a driving force. The driving force will be the formation of water, the formation of a gas, or the formation of a solid. There's no water in these formulas. There's no readily recognizable gas being formed here, so the only thing that's available to us for a driving force is the formation of a solid. Since you memorized the solubility rules, you should know that sulfates, while they are mostly soluble, they're not soluble when they're bonded with silver, so this is a solid, and that provides our driving force. We formed a solid. This over here is an acid, and chlorate compounds are always soluble. That's always going to be aqueous so long as there is water around, and we knew there was water around because both these compounds were dissolved in water, and that's why we called them aqueous. So there's our initial prediction of products. We need to balance the formulas. Sulfate has a 2 negative charge. Silver has a 1 plus charge, so we need 2 silvers. There's a 1 plus charge on the hydrogen, a 1 negative charge on the chlorate, so that's already balanced. We're ready to write our atom inventory. So right now we have 1 silver, 1 chlorine, 3 oxygens, and 4 is 7, 2 hydrogens, and 1 sulfur. On this side, I've got 2 silvers. I have 1 chlorine. I have 4 and 3 or 7 oxygens. I have 1 hydrogen and 1 sulfur. So we're going to wait to balance oxygen last and hydrogen next to last. We're starting with the silver. To get 2 silvers on the left, I'm going to use the coefficient in front of the species that contains the silver. And now I need to rebalance for everything in that formula. So I have 2 silvers now, 2 chlorines. The number of oxygens here is 2 times 3 is 6, plus this 4, that's 10 oxygens. All right, so we've got the silver balance. We have to balance the chlorine now, because we unbalanced the chlorine. To get 2 chlorines on this side, I need to put a coefficient 2 in front of the species containing the chlorine. Once your formulas are balanced, you can't change the formulas. Okay, you have to leave the formulas alone and only use coefficients to balance the equation. So this is going to unbalance the number of hydrogens and chlorines and oxygens. So now I have 2 hydrogens. I've got 2 chlorines. And I've got 4 oxygens here, plus this 2 times 3, or 6. So 4 plus 6 is 10, and the equation is balanced. Now we want to write a complete ionic equation. You have a question? While you can, it doesn't always work. Atom inventories always work. Okay, what she's asking about, the question was about, can you make an ion inventory instead of atom inventory? Ion inventories are possible, but only if you know when you can use them and when you can't. On the other hand, atom inventories always work, so I'm only going to teach, and I'm going to expect you to use an atom inventory every time. Okay? All right, so the complete ionic equation, I have 2 silver ions. If the original compound was aqueous, then we split up ionic compounds like this. We're going to show them as aqueous as well. I've got 2 chloride ions. Since I split them up, I'm showing the charges. This acid is aqueous. We're going to split it up. I've got 2 hydrogen ions and 1 sulfate ion. I'm going to tell you, I'm going to give you a partial equation. I want to tell you to finish it, and if there is a complete and net ionic equation, I may ask you to write one in that case. But you have to figure out if there is one. And the way you figure it out is only the double replacement and single replacement reactions have ionic compounds, and then only if there are aqueous compounds in there. All right, let's finish this equation. The solid doesn't change. We leave it exactly the same. We don't split it up. This is an ionic compound, or actually it's an acid. We have 2 hydrogens here, 2 hydrogen ions, and we have 2 chloride ions. All right. Now the net ionic equation then rewrites this equation, but only with the things that change. So the silver changes from a silver ion to the silver compound. We're going to keep the silver. The chloride ions don't change. They're exactly the same on both sides. We're not going to keep those. The hydrogen ions don't change. They're exactly the same on both sides. We don't keep those. The sulfate changes from this ion to this solid, so we're going to keep it. And there's the net ionic equation. All right, real quickly. Only double replacement and single replacement reactions can have ionic equations. Okay? So if I give you a combustion reaction, for example, there won't be a net ionic or a complete ionic equation for that. Okay? If I give you a synthesis reaction or a decomposition reaction, you'll assume there's not one. There actually can be sometimes. We're not going to deal with that here right this time. Okay? Any questions about that? All right. Now I want to make sure one thing is really clear that I'm not sure I made as clear as I'd like to. We said that if you have combustion reactions, you're always going to be starting with a hydrocarbon, and we're going to have oxygen. Okay? We won't be balancing any equations that fit this new category I'm going to talk about. But if I had this as part of this compound, it would still be a combustion reaction, because you got carbon and hydrogen in this compound and some oxygen to do the work. Okay? And this happens to be the chemical reaction that you're running in your body 24/7.